What section is this?
5.4. Recently we have looked at natural logarithmic function. And if we were going to look at the graph of that natural logarithmic function, we know that it looks something like this. All right, f of x equals the natural log of x. What can you tell me about the domain of this function, Sam? I don't know. Is it from negative infinity to infinity? What is it, Maddie? 0 to infinity. What's the range? Negative infinity to infinity. Remember, Sam, domain is your x's. All right, is this function strictly monotonic? How can you tell? Passes a horizontal line test. What else? And what else do we see about it that we know it's strictly monotonic? It's always increasing. All right, so this is a always increasing, strictly monotonic, so it does have an inverse function. And if it has an inverse function, what is the domain of the inverse? Negative infinity to infinity. And William, what's the range of the inverse? Why negative infinity? Okay, why? What made you change your mind? Besides me asking you a question.
I was just reading as a person. Probably because I don't know.
What's the relationship between the domain and range of a function and its inverse?
The inverse. It's like the opposite. Okay.
The opposite?
Flips.
They switch. All right. And so it reflects across the line y equals x. Is that right? Let me see if I can change colors here. Oh, I can do it here. All right. And so the inverse function would probably look like something along those lines. And this is the natural exponential function.
Does it have any bounds then, or is it just infinite on the domain and range?
Okay, the range is from 0 to infinity. It approaches the horizontal, the x-axis. The domain, the domain is from 0 to infinity. No, wait. Domain is negative infinity to infinity. Range is 0 to infinity. All right, so the inverse function of the natural log is the natural exponential function, which we looked at last year. Now, if these functions are inverses of each other, then that means that if I take the composition of the function and its inverse, I should get what? X. So that means that the natural log of e to the x equals what? X. And if we go the other way and I take the composition this way, we should get x if these are truly inverses. And so e to the natural log of x equals. Now these relationships can save you some time if you will remember those when we work with problems. I'm going to go through this kind of quickly because the first part of what we're talking about is review from last year. We looked at exponential functions and logarithmic functions last year. In fact, I think we did exponential functions first. And if we want to convert from an exponential equation or to solve an exponential equation, for instance, if we have 7 equals e to the x plus 1. Now, if you had a calculator handy, you could put e to the x plus 1 in y1, y7 and y2 and see where they intersect. But if you don't have that graph handy, we can solve this by taking the natural log of both sides. And if we do that, we get the natural log of 7 is equal to the natural log of e to the x plus 1. So this side becomes, the right side becomes what? X plus 1 based on what we just saw right here. So we have the natural log of 7 minus 1 equals x. And you could, if you need an answer, a decimal answer, you can just plug that into your calculator. This is approximately 0.946, just a calculator answer. If you're asked for an exact answer, then you give it this way. Remember doing this last year? A little bit. If you had 4e to the x equals 83. Before you take the log of both sides, you want to divide by 4. Isolate the exponential term. So e to the x equals 83/4. Remember, I'm trying to solve for x here. So Michelle, what can I do? Take the natural log of both sides. So when we take the natural log of e to the x, what does the left side become? X. And now from this point, you could just get a decimal approximation.
You have to show the stuff about when the x, can't show stuff because first two.
I would, if you're doing this on the exam, I would.
Okay.
All right, let's look at a different type of equation. If we have the natural log of 2x minus 3 equals 5. Do you remember how we solved this type of equation for x? Again, we did this last year. But, okay. Your book tells you can exponentiate both sides. In other words, you can do e to the natural log of 2x minus 3 equals e to the 5th. And so what does the left side become? 2x minus 3 equals e to the 5th. And then you can simply solve from there. 2x equals 3 plus e to the 5th. And x is equal to 3 plus e to the 5th divided by 2. Your other option is to just rewrite it in exponential form, which basically you're doing the same way. From right here, you could say the base is e to the 5th equals 2x minus 3. Here, I don't care which way you do it. Makes a little bit more sense to me just to rewrite this as an exponential statement. You're doing the same thing. So, if we have the natural log of x squared equals 10, you solve that one. X equals plus or minus the square root of e to the 10th. Because you get e to the 10th equals x squared. Anytime you have an equation and you're taking the square root, you have a positive and a negative root. Okay. No. If it were e to the I'm not even sure if it was e to the 25th. I guess if it was e to the 25th, it might be e to the 5th. Let's look at the derivatives of the natural exponential function, which I think we've already kind of talked about. But these are some of the, like the natural log was easy, these are very, very easy to take the derivative. If u is a differentiable function of x, then the derivative of e to the x is simply e to the x. Or if we are taking the derivative of e to the u, in other words, use some differentiable function. It's not just x. This is going to be e to the u du dx. Wait a minute. E. Yes, it would be. I'm sorry. Because it's e to the 10th to the 1/2. It would be. Sorry about that. You're exactly right. You could rewrite this as x equals plus or minus e to the 10th to the 1/2, and it would be to the 5th. I'm sorry. I wasn't thinking very clearly there. Thank you, Andrew. All right, so let's look at the derivative of e to the 2x minus 1. What is the derivative of the u part? 2. So this becomes twice e to the 2x minus 1.
Which rule justifies
That rule. E to the u du. E to the u times the derivative of u. This is your u.
So like we said earlier in the warm-up, like you take the derivative of that put it in front. So basically it's just the du dx is in front of the u.
In this case, yes, I put it in the front. I want to take the derivative of e to the negative 3 over x. So what are you going to have to find first, Michelle? Okay. So the derivative of u is, we said what, 3 over x squared? Times e to the negative 3 over x.
Yeah.
Yes. Let's look at integrals. Any questions on the derivatives? All right, integrals are easy as well. Justin, are you okay?
Yes.
You don't just get up in the middle of class and walk out. And you still don't get up and walk out unless it's an emergency. Okay, what about this one, Curtis?
Okay. Negative 2x is what you need.
Mm-hmm.
That's the derivative. But you have a 5x.
Mm-hmm.
So I'm thinking you're going to do something with 10x.
With 10x. What can we do with this to start with?
Oh, factor out a 1 or a 1/5. Or 5. 5.
Maybe a 5. What happens in here?
You get a 2, -2.
Okay. So now I've got my du. So we have e to the u du. We're okay? So what do we get when we integrate?
5 over 2, -5 over 2, e to the negative x squared plus c.
Is he correct?
Yes.
Just work a few more. That one looks kind of funny. Sam, what do we need to do here?
Well, I need to substitute, I need to find u and u.
Okay, what is u then? If you're going to substitute, what's u?
X squared. And then you can find x, you can have an x.
So do you think x squared is my u?
Or get 2x.
Du would be 2x. Do I have that, or is there any way I can get that?
Why don't we take the derivative of 1 over x?
Why do you think you'd do that, Curtis?
That's how you're supposed to do it.
I don't know. I mean,
E raised to u
okay.
equals du over dx. Or wouldn't you have to find the derivative of 1 over x instead of x squared?
Okay, so let's try it that way and see what happens.
Just want u equal 1 over x instead.
If u is 1 over x, which is the same as what?
X to the -1. Wait.
All right, so what's the derivative of that?
Negative x.
Negative x to the -2, which is negative 1 over x squared dx. Do we have that? Almost. I just need a negative. So if I put in a negative here and a negative here, this becomes negative what?
E to the 1 x plus c.
See the difference, Sam?
Yes, I do.
Okay. Since, especially since we're talking exponential functions here, that's where you look first. All right. Trying to just give you some different examples. All right, sine x e to the cosine x dx. William, what do you think?
Okay. You obviously have to do something with the cosine.
What do we have to do about the cosine x? Which is what?
No, not chain rule.
What's the derivative of
Oh,
cosine x?
sin x, next sin x.
So do I have that?
No, we'll find an 8-1.
Okay, so but almost if I put a -1 in, then I'm okay.
Okay.
So what do we get when we integrate?
Negative e cosine x.
Negative e cosine x plus c. Let's do a definite integral.
So this is kind of new material, but not really. We're just looking at e.
Okay. Just a new thing to integrate.
And the e's natural log.
It is the inverse of the natural log. All right, we're going to integrate from 0 to 1, e to the x over 1 plus e to the x dx.
one you have to use synthetic division.
The natural log of what? E to the x?
1 plus EX.
And how did you determine that that was the case?
The derivative of that is derivative over the original.
Okay, and we have the derivative of the denominator is e to the x, so we have u prime over u. Good. So this becomes a natural log of 1 plus e to the first.
Wait, so 1 plus e to the x is the derivative of e to the x? Yeah.
No.
No, e to the x is the derivative of 1.
Anytime you see a quotient, you do want to check, do I have the derivative of the denominator in the numerator? If not, then you've got to do something else, but in this case we do. And we didn't even have to manipulate it.
Wait,
Okay.
so how is the derivative? Are we supposed to know what ex is? Like, because if you divide not like 1, it's just 0.
Yeah,
Do what?
if you derive e to the x, it's e to the x.
It's e to the x.
We're supposed to know.
Yeah.
Yeah. William says, yeah, like we really should know that, right? Okay, so here we have the natural log of 1 plus e minus the natural log of what?
1 plus e.
1 plus 1 is 2. And so you could get a approximation for this, which is approximately 0.620.